This talk is a skeptical view of fusion research based on my long career as a fusion physicist. I will start with a general introduction to fusion and then describe the tokamak, which has been the most successful fusion device so far, but I will emphasize its many problems as a potential fusion reactor. Then I'll briefly mention some of the other fusion devices being tried at this time, and finally I'll conclude with an answer to the question, will fusion work? First, let me describe some of the origins of current fusion research. About 1920, astronomer Arthur Eddington hypothesized that the stars are powered by nuclear fusion reactions, although there was very little evidence for this at the time. But by 1938, physicist Hans Bethe developed specific models for how a chain of fusion reactions could liberate energy in the core of the Sun. This is still the basic mechanism believed to power the Sun and the stars. Ideas for a fusion bomb were developed during the Manhattan Project of World War II, and by 1952 the first hydrogen bomb was tested with a huge yield of about 10 megatons of TNT. This was a very quick success and led the scientists of the time to be optimistic about building a controlled fusion reactor to create electricity. Now I will describe attempts to create controlled nuclear fusion. In theory, there is enough fusion fuel in the oceans in the form of deuterium to provide electrical power for mankind for millions of years. However, this fusion fuel needs to be heated to about 100 million degrees centigrade, hotter than the center of the Sun, in order to start significant fusion burning here on Earth. By the early 1950s, the first tabletop fusion experiments briefly reached about 1 million degrees, as illustrated in the photos at the top right. By the 1990s, house-sized experiments, as shown at the photo at the bottom right, finally reached the required 100 million degrees. So what's the problem? This slide gives an overview of the problems of fusion in general, independent of the configuration of any proposed reactor. The first problem is the physics of plasma, the rapidly moving hot gas which constitutes the fusion fuel. This complex physics needs to be well understood in order to efficiently control any fusion reactor. The next problem is the engineering of such a fusion reactor, which requires pushing the thermal and mechanical limits of known materials, such as those which need to surround the extremely hot plasma. Safety is obviously a major concern for any nuclear technology. A fusion reactor will almost certainly become highly radioactive and will have to be maintained remotely and robotically. To be practical, the cost of any fusion reactor will have to be comparable to the alternative sources of electricity. This is difficult due to the complexity of fusion devices compared, for example, with solar and wind power. Although none of these general problems completely prohibits a fusion reactor, solving them all together in a single device will be very difficult. The next part of this talk will describe a specific fusion device called the tokamak, which is a Russian term for a toroidal or donut-shaped magnetic chamber. This has been the most successful fusion device since its invention in the 1950s. Over 100 tokamaks have been built around the world since then, and I myself worked on 7 different tokamaks from 1974 until my retirement in 2018. The diagram at the left shows a schematic view of a tokamak with the plasma in orange and the magnetic field coils in blue. The plasma follows the magnetic field lines around the donut. The photo at the right shows the inside of the jet tokamak during a maintenance period, with a man in a protective suit for scale. Until recently, this was the largest tokamak in the world. This slide lists 10 of the major problems for a tokamak reactor, all of which will be discussed in more detail in succeeding slides. The first 5 are problems for existing tokamak experiments, and the last 5 are problems for future tokamak reactor designs. Each of these problems has been well known and extensively studied for over 40 years, but none of them have been solved yet. The first problem is plasma confinement, which has been the main physics issue in tokamaks for many years. Hot fusion plasma moves it up to about 1,000 kilometers a second, so it must be very well confined, or else it will hit a wall and cool off before significant fusion can occur. The plasma energy can be guided using a strong magnetic field, as illustrated in the photo of a solar flare at the bottom left. The giant plasma flare ejected from the sun's surface is turned around into a loop by the sun's magnetic field. Similarly, a plasma can be fairly well confined in the magnetic field of a tokamak, as shown at the bottom right, sometimes described as a magnetic bottle. But the energy confinement time of the largest existing tokamak is only about 1 second, which is much less than the confinement time needed for a tokamak reactor of about 5 seconds. The energy confinement process is not well enough understood yet to predict the energy confinement time in a future reactor-sized plasma. The best fusion fuel is a near 50-50 mixture of deuterium and tritium, which has an optimum reaction rate at about 100 million degrees centigrade. There will also be some impurity atoms in the plasma coming in from the wall. However, tokamak reactors can tolerate only about 0.01% of tungsten wall atoms before fatal cooling occurs due to atomic radiation. The photo at the right shows visible radiation coming from a tokamak. The radiation cooling from the tungsten will be mostly due to X-rays from the core. In addition, helium ash atoms from the DT burn itself will dilute the fuel and reduce the fusion power, depending on how long this ash is confined inside the plasma. The impurity and helium ash content cannot yet be predicted for a tokamak reactor. All tokamaks have violent plasma disruptions when the plasma explodes within a fraction of a second and hits the wall, ending the tokamak pulse. The physics of this instability has been studied for over 40 years, but there is still no foolproof way to predict or prevent these disruptions. A video of a tokamak pulse with a disruption at the end is shown at the right. The disruption causes a shower of sparks when the plasma hits the wall. I'll play this twice so you can see the disruption 2 times. Larger plasmas have more energy and could cause significant damage to the inner wall surface. In a tokamak reactor, a single large disruption could blow a hole in the wall and cause a loss of coolant accident, which could decommission the reactor, perhaps permanently. Gradual erosion or melting of the inner tokamak vacuum vessel surface is inevitable due to the continuous plasma particle and heat loss. The expected wall heat flux will be close to the thermal limits of the strongest first wall material, tungsten. The photo at the right shows laboratory testing of tungsten wall tiles under plasma heat and particle bombardment. Due to this gradual erosion, at least some of the reactor inner wall surface will need to be replaced every few years, which would be a very difficult and costly operation. Almost every tokamak experiment has had a major magnet failure, including the recent billion-dollar superconducting tokamak in Japan in 2021. These magnets can fail due to coolant leaks, mechanical stress, or electrical arcing, but failed superconducting magnets in a tokamak reactor cannot be replaced after DT starts due to the high radiation levels and huge costs of replacement. At the bottom is a photo of a single next step tokamak superconducting magnet with some of its builders standing inside of it for scale. All of the tritium fuel in a tokamak reactor must be created within the reactor itself, since tritium radioactively decays in 12 years and so is not found on Earth. In principle, just over 1 tritium atom can be bred in the wall for each fusion neutron, but this requires nearly the whole inner wall to be covered by a nuclear breeding blanket. At the right is a schematic of a possible tokamak blanket design. The design of these blankets is extremely complicated due to neutronic, thermal, and mechanical interactions, and none has been tested so far in a DT environment. DT fusion reactions create high-energy neutrons, which penetrate up to 1 meter into the blanket structure. These neutrons microscopically displace atoms in the wall, probably based on steel, and will eventually damage its crystal structure. Below is a schematic picture of the atoms in a crystal lattice being bombarded by neutrons in a tokamak reactor wall. After a few years, every atom of the fusion reactor wall will be displaced on average about 100 times, which will greatly weaken its structure. This damage will require blanket replacement every few years in a tokamak reactor, which must be done robotically while the tokamak is shut down. This is a major operation considering the cost and complexity of the blanket. By 2023, the best tokamak made about 10 megawatts of DT fusion power for about 7 seconds, as shown in red in the figure below. But this was only done a few times a year, and of course the electrical power needed to make these pulses was very much larger than 10 megawatts. The next major tokamak ITER is planning to make about 500 megawatts of fusion power for up to 7 minutes, at most once a day, as discussed later in this talk. But a real fusion power plant would need to make about 3,000 megawatts of DT power for at least 10 hours a day every day for many years. This is an extremely big but necessary step to achieve a practical fusion power plant. A tokamak reactor will contain many kilograms of radioactive tritium, which must be very carefully handled to avoid public exposure. But tritium is not as dangerous as radium or plutonium. For example, tritium has been used to make watch dials glow, as shown in the figure. Another problem is that thousands of tons of radioactive waste will be created in a tokamak reactor due to neutron activation of the wall. This will require decommissioning and long-term storage after the reactor's lifetime. But this waste ought to be easier to handle than the high-level nuclear waste from a fission plant. A less well-known issue is that fissile, or explosive nuclear fuel, can be made by exposing natural uranium to DT fusion neutrons, which creates a potential risk of nuclear weapons proliferation. Probably the biggest problem for a tokamak reactor is its very high and very uncertain cost. Large fusion power plants would very likely require expensive nuclear licensing and government regulation, similar to fission power plants. The untested technology of fusion reactors implies a highly uncertain electricity cost until their operation can be demonstrated extensively. It's nearly certain that fusion power will never be cost competitive with solar or wind energy, which are infinitely simpler and work well now. The ITER tokamak is the largest fusion research project ever funded. Its construction started in 2013, and DT operation is planned for 2035, with a total cost of about $50 billion. One of its 9 large vacuum vessel segments is shown in the photo to the right, with people standing near the bottom for reference. ITER will be about 30 meters tall. ITER might make 500 megawatts of fusion power, but this could be converted to only about 200 megawatts of electrical power, which is about what it will need to run itself. Thus, ITER could never make any net electricity. A demo tokamak would aim to put electricity onto the grid, maintain tritium self-sufficiency, and try to demonstrate safe and cost-effective operation of a prototype fusion power plant. An artist's impression of a demo tokamak is shown at the bottom. It has a generator to convert the fusion heat to electricity, which ITER will not have. A demo reactor would be very much more difficult to build and operate than ITER. It would be one of the hardest technological challenges ever. So what is the likelihood that a tokamak reactor will succeed? At the left is our list of problems with guesses as to the likelihood that they will be solved based on experience of the past 40 years. None of these has a likelihood of more than about 1/2, or else they wouldn't be there. The least likely are about 1 in 8, which is highly optimistic for some of them, such as cost competitiveness. If so, the overall chance that all of these nearly independent problems will be solved together in a practical tokamak reactor is the product of these likelihoods, or roughly 1 in a million. Even though the tokamak is very unlikely to succeed, it is still the leading fusion candidate based on its high power output and worldwide database. Other magnetic fusion concepts aim to solve some of these problems, but their fusion power output has so far been much below that of tokamaks. The next best device, the stellarator, is similar to a tokamak but much more complicated. Inertial confinement fusion may be scientifically interesting, but not credible as a practical reactor due to intractable problems of driver efficiency, target cost, target alignment, chamber clearing, and tritium breeding. My conclusion is that fusion reactors are unfortunately not going to be a practical source of electricity in the future. This is mainly due to the complexity and difficulty of fusion compared to the simplicity and lower cost of other options.